Welcome to this lecture of this course on machine learning using Python programming. In the previous lecture, we have seen multiple linear regression, and in this lecture we will see polynomial regression. So, we will see what is the difference between linear regression and in that simple linear regression and multiple linear regression, and now we are going to see polynomial regression. So, in case of simple linear regression or multiple linear regression, the assumption is there is linear relationship between dependent variable and independent variables. In case of simple linear regression, there was only one independent variable. In case of multiple linear regression, there are more than one independent variables. So, here we can see in the first figure, this when we are plotting our data set. So, this is showing the linear relationship between x and y. So, if we will create multiple simple linear regression model, so we may get suppose this line as a model. So, it is well fitting the data that is given. While if your data when you are plotting is like this, we can see here that relationship between x and y is not linear according to the data that is given, because this plot is not suggesting us the linear relationship. But if we are trying to model relationship between x and y using simple linear regression, so your model may be like this, and you can see here your predictions error is large in this case, because there are only 3 points in this case that are very close to the line, or so predicted value and actual values are close only for these 3 points, and for rest of the cases your actual value is this and predicted value is here. So, this difference is very high. So, we can say that sum of squared prediction error will be very high in this second case. So, if relationship between x and y is not linear, in that case we must have some other way to find the model, to fit the model, so that we can fit non-linear model, or we can learn the non-linear relationship between x and y. So, you see, if we can learn this model, so this model is non-linear model and it is very well fitting all the data. So, all these data are very close to the model. So, you can say here the difference between actual and predicted is less for most of these, and even for we can say all of these data points in our data set. So, it means if there is non-linear relationship between x and y, then we should use some non-linear models, and polynomial linear regression is one of them. So, when simple linear regression would not be relevant, it means your data set is non-linear data set. In that case, we can use polynomial linear regression. So, we can use a linear model to fit the non-linear data. So, how we can do this? We will add powers of each features as a new feature. So, and then train this linear model on this extended set of features. So, whatever data set you are having, in that data set, suppose you are having 10 features. So, you will extend your data set by adding few more features that are corresponding to the square or cube or multiplication of two features, that is x1, x2 and so on. So, what we do here, we use a linear model to fit non-linear data. So, how we do it? We add powers of each features as a new feature and then train a linear model on this extended set of features. So, we can say that if in your data set you have suppose 10 features, so you will add few more features and these newly added features are nothing but you will take different powers of the existing features and that you will add as a new feature. So, this technique is called as a polynomial regression. For example, you see here y is equal to b naught plus b1 x plus b2 x square plus b2 b3 x3 and so on. So, in this case there is suppose only one feature, only one independent variable x, but relationship between y and x is non-linear. So, our model, we cannot take the model as y is equal to b naught plus b1 x. In this case we will add few more features, that is suppose x square, x cube and so on, and in that case our model will now become y is equal to b naught plus b1 x plus b2 x square plus b3 x cube and so on. So, we will need to decide how many powers we are going to add in our model or how many new features that are corresponding to different powers of these independent variable we are going to add in our model. So, why we are saying this is this as a polynomial linear regression, while it is learning or it is showing the non-linear relationship that is present in the data set. So, why it is linear? Because we are defining this linear in regards to the coefficients, not to the independent variables. So, here you see b naught, b1, b2, b3 and so on. So, these are the coefficients and there is no power of these. So, that is why we are saying it is a linear. So, the no independent variables power we are having. So, we are not defining it in terms of number of independent variables, we are saying it is linear in terms of coefficients. So, we can say now it is a special case of multiple linear regression. So, in case of multiple linear regression, x was first feature and then the variable corresponding to coefficient b2 was the next feature. So, here next feature is x square, that is generated through x only by taking power square of that feature. So, now if we take x as the first feature, x square as the second feature, x cube as the third feature. So, this is nothing but multiple linear regression. So, generally these when there is a non-linear relationship, then we use it. So, one of the use case is when we need to describe how diseases spread across the population. So, in these cases, this type of case we use polynomial regression. So, in case of we have seen the example where we had the single feature x. So, in that case what we have done, we added new features as the different powers of x. But if we have more than one features in our data set and there is non-linear relationship between y and suppose x1, x2 up to xn, in that case how we will apply polynomial linear regression or how we will create our model. So, in this case polynomial regression is capable of finding relationship between features, and this is made possibly by the fact that it adds all combination of features up to the given degree. So, relationship we can get from the coefficients of these newly added features having combination of different features. So, what we are doing, suppose if there are two features a and b and we are selecting 3-degree polynomial. So, how many features we will add? We will in that case definitely we are already having a and b. So, we will add a square, a cube, b square, b cube, but we will also add few more combinations because our degree of polynomial is 3. So, we will add a b, a square b and a b square also. So, that is why when we will see the coefficient of a b or coefficient of a square b or coefficient of a b square, so it will give us the relationship between a square and b or a b square or a b. So, multiple linear regression, as we have seen, it also helps in finding the relationship between features. So, by seeing the coefficients of those terms where more than one features are present like a b, a square b or a b square, we can find relationships among them. So, it we can say it transforms an array containing n features into an array containing n plus d factorial upon factorial d factorial n features. So, here d is the degree of the polynomial. So, if we are taking large degree polynomial, in that case number of features we will need to add, and we may have high dimensionality because of your high dimensional data, and there may be another problem because of that we have seen, and we need to take care of that using dimensionality reduction. So, this is different. We need to check what should be the degree when we are talking about polynomial regression, but this is the way we do polynomial regression in case of multiple features. So, what is the physical significance of coefficients that we have in polynomial regression, where we have more than one independent variables in the original data set? So, in case of simple linear regression or multiple linear regression, each coefficient basically represent contribution or effect of that particular term on model's prediction. For example, we have seen if in case of simple linear regression, our model is y is equal to b naught plus b1 x. In case of multiple linear regression, the model is b naught plus b1 x1 plus b2 x2 plus b3 x3. So, we are assuming there are 3 independent variables. So, our model is y is equal to b naught plus b1 x1 plus b2 x2 plus b3 x3. Now, we can say the value of these coefficients tells us how much significant that corresponding independent variable is. When we are learning these coefficients values, after learning, suppose b1 is 0. If b1 is 0, it means it is suggesting that there is no relationship between y and x1, or we can say that y is not depending on x1. So, for all those coefficients where value is very small, we can say that corresponding independent variables are not that much important, and we can leave them. And for those coefficients where value is very large, those independent variables are important in explaining the variability in y. So, it means there is good relationship between y and that independent variables. So, this was the case of simple linear regression and multiple linear regression. So, here coefficient values gives us the idea about significance of independent variables or significance of predictors. Now, we will see what is the physical significance of coefficients in polynomial regression case. So, in polynomial regression, you may have one term that is corresponding to x1 square, and then another term that is corresponding to x2 square, as we have seen here. So your model can be y is equal to b naught plus b1 x1 is square plus b2 x2 is square and so on. So in that case we are trying to now see what is the physical significance of those coefficients that are of squared terms, x1 is square, x2 is square, x3 is square. So coefficients of these squared terms, what is the meaning of that? So these terms in the model basically non-linear relationship, definitely there is a non-linear relationship between y and x1, that is why squared term we are adding. There is non-linear relationship between y and x2 also, that is why x square term is added in our model. So x square means that feature x1 affects the target in quadratic fashion. So means x1 independent variable affects the dependent variable in quadratic fashion, because x1 is square term we are having in our model. So the corresponding coefficient quantifies the curvature of the relationship between x1 and the target variable. So if this coefficient is positive, you can say that your this concave is upward, U-shape relationship curve you will get, and if this coefficient is negative, coefficient corresponding to x1 square or coefficient corresponding to x2 square. So it means this curve, concave is downward. So using by seeing the coefficients corresponding to these squared terms, you can get the idea of relationship, idea of the curve that is showing the relationship between dependent variable and these features whose squared term we are seeing here. Now we will see the physical significance of coefficients of cross product terms, like in our model we may have y is equal to b naught plus b1 x1 plus b2 x2 plus b3 x1 x2. So b3, what is the physical significance of b3? That is coefficient of x1 x2 or any product term. So this coefficient basically this x1 x2 is giving you the interaction between two features x1 and x2. So we can say that this term is giving the relationship between dependent variable and interaction of x1 x2, interaction of that with x1 x2 together. So it indicates the effect of one feature on target variable depends on value of other feature also. So both x1 and x2 both defines dependent variable y. You can't say if you will change x1 then y will change like this. We will need to check what is the value of x2 also, because x1 and x2 together are defining y according to this term. So coefficient of this term represent magnitude of interaction. So if the coefficient is positive, we can say that increasing both x1 and x2 together will increase target more than the sum of their individuals effects. So if you are increasing x1 and then y is suppose also increasing, and you are increasing x2, y is also increasing. So this term x1 x2 term, if this term is there in your model, so by seeing the coefficient you can say when we will increase both of these two, then the target variable will increase more than the sum of their individual effects. In the same way, if coefficient is negative, in that case increasing both x1 and x2 together will reduce the target more than the sum of their individual effects. So this is the physical significance of coefficients of the cross product terms. So if you suppose you are learning a model, and in your model the coefficient corresponding to x1 x2 is 0, it means there is no interaction between x1 x2, or you can say that x1 may independently it is defining the behavior of y. Similarly, x2 may independently, but these two together, these are not defining the behavior of y. So, y is not depending on both of them together. So, now we will see the physical significance of coefficients that are of higher order interaction terms, means x1 is square x2, or x2 is square x1, or x1 is square x2, x3 is square, and so on. So, these we can say these coefficients or these terms represent more complex interactions. You see, x1 is square x2. So, this is giving you interaction of x1 is square and x2. So, you can say this is the interaction that showing how the squared value of one feature interacts with another feature. So, coefficient of that will give you this will give you information regarding this complex interactions of x1 square and x2. And so, now after seeing the physical significance of different coefficients in the polynomial linear regression, we will see that polynomial regression is not non-local. So, polynomial regression is non-local means when we are we will do some changes in the model, then there will be that change will not be local. If we will change in one feature, so or in one instance, so it is not the case that corresponding y value or the instances that are close to this instance, their y value will only be changed there. So, your model will change only y values of those instances. It is not the case. We will see, because polynomial regression is non-local, while some other algorithms like KNN, these are local algorithms. So, we will see in detail what is difference between these two. So, when we talk about changes to the polynomial, so there are two ways we can change, we can do changes in our polynomial. So, one is we can change in the coefficients, and another is we can change in the degree of the polynomial. So, in this way these two we can change in our polynomial. So, suppose we are changing in the polynomial by changing coefficients of the polynomial. So, we have already seen the significance of these coefficients. So, we can say that a small change in any of the coefficient can reshape the curve. For example, we have seen the coefficient of squared terms, and this coefficient is giving you the curvature of that curve. So, if you will do a small change in those coefficients, so your curve shape will be changed, it will reshape the curve significantly, and it will affect the prediction across the entire feature space. So, it is not the case that only for the few instances predictions will be now different. For rest of the instances your predictions will be same as it was earlier before changing that particular coefficient. Your there are chances that all the predictions will be changed. So, this is the way we say that polynomial regression is non-local. We are changing only in one coefficient. For example, if we change a coefficient beta 2, and suppose this coefficient is the coefficient of x2. So, x2 is one of the feature, and we are changing only its coefficient. So, we are if beta 2 increases, so we are increasing this coefficient. So, curvature of the quadratic term becomes steeper, and since curvature of this quadratic term becomes steeper, so definitely it will affects the model's behavior across the entire input space. So, for many instances your prediction will be now different. In the same way, if we are changing beta 1, that is the linear term, so it would alter the slope of the entire regression. So, if slope will change, then definitely it is its effect will be non-local. It means it will change the prediction of many of the instances. The second way of changing polynomial is we can change the degree of the polynomial. So, suppose initially we have taken degree 3. So, in that case few terms we added in our model. So, a square, b square, then a cube, b cube, a square b, b square a, and so on. So, but if we will increasing the degree of the polynomial, suppose we are making it now 4. So, we will add few more features, a cube, sorry, a to the power 4, b to the power 4, a cube b, b cube a. So, in this way, since we are including more terms, so definitely it will change the model, and again you will have lot of differences in predictions for all the instances. So, again these changes will be non-local. So, you can see here a quadratic model, that is x square, it can fit parabolic, this is x square not x2. So, this is mistake in typing, this is x square. So, in quadratic model, a quadratic model can fit parabolic shape, while a cubic model can fit S shape curve. So, if we are increasing the degree, so our shape of curve is again changing, and because of that you can say your model is totally changing, and your predictions are now getting changed. So, so we can say that higher degree polynomials fit curves that oscillates more, and so they blend and twist around the data points, and sometimes you can say they may better fit the data, sometimes there may be problem of overfitting. So, there is always this is we can say we need to decide what degree of polynomial we should take in our model, because if we are taking large degree of polynomial, in that case there may be chance of overfitting, and if we are taking less degree polynomial, in that case you may not be able to capture the actual relationship between y and x, or you may not capture the complex patterns in your data. So, influence of the data point, as we will see difference between non-local and local. So, as we have seen, polynomial regression is non-local, while we will see another machine learning algorithm, that is k nearest neighbor. So, this is this k nearest neighbor is basically used for classification purpose. When we will see classification, we will see how it works. So, KNN is purely local, and we will see that time if we will change something in the model, it will change in the predictions of only few instances. So, that is purely local, while in case of polynomial regression, we have seen if we are changing any coefficient, or if we are changing in the polynomial by adding degree, in that case lot of changes occurs in the prediction of many of the instances, and that is why it is non-local. So, now we will see pros and cons of polynomial linear regression. So, first of all, it works on any size of data set. It works very well on non-linear problems, and that is why we are using it, otherwise we can use multiple linear regression also. Then we will need to choose the right polynomial degree for a good Bayes variance trade-off. I already told you that when if we will take a high degree polynomial, in that case there may be chance of overfitting. You are taking low degree polynomial, in that case you may not capture the complex patterns in your data set. So, this is the difficulty in case of polynomial regression, that you will need to decide what is the right polynomial degree. Then it is inherently non-local. So, changing the value of y at one point in the training set can affect the fit of polynomial for data points that are very far away. So, while in case of KNN, if we will change only in one instance, so it will the predictions of other instances that are very close to this instance will only be changed. Predictions of other instances that are far away from this will not be changed. So, that is local to change, while this polynomial regression is inherently non-local. So, to avoid this, the use of high degree polynomial on whole data set, what we do sometimes, we substitute it with many different small degree polynomial functions, means we divide our data set in different sets, and then for these different groups we will learn the small degree polynomials. So, we will have many models, but for different subgroups of the data set. So, in this lecture we have seen polynomial regression, and we have seen when we need it, and how these are the coefficients of the polynomial regression, what is the physical significance of these polynomial regression, why it is non-local in nature, and when we should use polynomial regression. So, I am stopping here. I hope you enjoyed this lecture. Thank you.